Welcome to EPG Pathshala. The name of this module is Ancillarity. The concept of ancillarity was introduced by R.A. Fisher in the year 1925. It plays a very vital role in the theory of statistical inference. The ancillary statistic lies in the opposite pole of a sufficient statistic in the sense that a sufficient statistic contains full information about the unknown parameter theta, whereas an ancillary statistic contains no information about theta. We discuss some examples relating to ancillarity, and finally we shall prove a very important theorem in statistical inference, which is known as de Basu's theorem. The concept called ancillarity of a statistic is perhaps the furthest away from sufficiency. A sufficient statistic Tx preserves all the information about theta contained in the data x. To contrast, an ancillary statistic Vx by itself provides no information about the unknown parameter theta. Individually, an ancillary statistic would not provide any information about theta, but such statistics can play useful roles in statistical methodology. The term ancillary statistic, from the Latin ancilla meaning handmaiden, was introduced by R.A. Fisher in the year 1925 in the context of maximum likelihood estimation. We first define an ancillary statistic. A statistic Vx whose distribution does not depend on the parameter theta is called ancillary for theta. Let us consider the following examples. Example 1. Let x1, x2 up to xn be independently distributed rectangular theta, theta plus 1 variables where theta belongs to real line. Let x ordered 1 less than x ordered 2 up to less than x ordered n be the ordered statistics for the sample. Now the sample range, which is given by capital R equals to x ordered n minus x ordered 1, is ancillary for theta. To prove this, let us define zi equals to xi minus theta for all I from 1 to n. Then zi follows rectangular with parameters 0 and 1 for all I, and hence the distribution of zi is independent of theta. If z ordered 1 less than z ordered 2 up to less than z ordered n be the ordered statistics for zi's, then capital R equals to x ordered n minus x ordered 1, which is actually z ordered n minus z ordered 1. Since the distribution of zi is independent of theta, the distribution of R is also independent of theta, and hence R is ancillary for theta. We consider second example. Let x1, x2 up to xn be independently distributed rectangular 0 theta random variables where theta greater than 0. Let x ordered 1 less than x ordered 2 up to less than x ordered n be the ordered statistics for the sample. Then the statistic capital V, which is the ratio of x ordered n and x ordered 1, is ancillary for theta. To prove this, let us define zi equals to xi by theta for all I from 1 to n. Then zi follows rectangular 0 1 for all I from 1 to n, and hence the distribution of zi is independent of theta. If z ordered 1 less than z ordered 2 up to z ordered n be the ordered statistics for zi's, then V equals to x ordered n by x ordered 1, which is z ordered n by, which is equals to z ordered n by z ordered 1. Since the distribution of Zi is independent of theta, the distribution of V is also independent of theta, and hence V is ancillary for theta. Next, we consider third example. Let x1, x2 up to xn be independently distributed normal random variables with mean theta and variance 1. Here theta belongs to real line. Then summation over I from 1 to n xi minus x bar whole square and summation over I from 1 to n mod xi minus x bar are ancillary for theta, where x bar is equals to 1 by n into summation over I from 1 to n xi, which is the sample mean. To prove this, let us define Zi equals to xi minus theta for all I and wi equals to xi minus x bar for all I. Then Zi follows normal 0, 1 for all I and Z bar follows normal 0, 1 by n. Both have the distribution independent of theta. As wi equals to Zi minus Z bar for all I, the distribution of wi is also independent of theta. Hence, summation over I from 1 to n wi square and summation over I from 1 to n mod wi are ancillary for theta. Next, we consider the fourth example. Let x and y be independently distributed random variables such as x follows exponential with mean theta and y follows exponential with mean 1 by theta respectively. Then the distributions of z equals to x by theta and w equals to theta into y are independent of theta. If we define v equals to x into y, which is equals to z into w, then the distribution of v is independent of theta and thus v is ancillary for theta. Next, we consider our fifth example. Let x, y be jointly distributed random variable with bivariate normal distribution with means 0, 0, variances 1, 1 and the correlation coefficient rho. Since x and y have individually both standard normal distributions, it follows that x is ancillary for rho and y is also ancillary for rho. We consider our sixth example. Let x denotes the number of points obtained in throwing a biased die and the probability distribution of x be given by probability under theta x equals to 1. This is equals to 1 minus theta divided by 12, comma, probability under theta x equals to 2, which is equals to 2 minus theta divided by 12. Probability under theta x equals to 3, this is equals to 3 minus theta divided by 12. Probability under theta x equals to 4, this is equals to 1 plus theta by 12. Probability under theta x equals to 5, this is equals to 2 plus theta by 12. And finally, probability under theta x equal to 6, this is equals to 3 plus theta divided by 12. If we define a random variable v such that v equals to 0 if x equals to 1 or 4, v equals to 1 if x equals to 2 or 5, and v equals to 2 if x equals to 3 or 6, then the distribution of v is independent of theta and hence v is ancillary for theta. Next, we consider a very interesting example due to D. Basu. Let x be a random variable with PDF. F theta x equals to 1 if theta less than equals to x less than theta plus 1, where theta is non-negative. Let us define v equals to x minus box x, where box x denotes the greatest integer contained in x. Then it can be shown that v has rectangular distribution with parameters 0 and 1. Since the distribution of v is independent of theta, v is a ancillary statistic for theta. Next, we consider a very nice theorem which was due to D. Basu in the year 1955. This is popularly known as Basu's theorem. Consider two statistics, capital T and capital V, such that T is complete sufficient for theta and V is ancillary for theta. Then V and T are independently distributed. Let us consider a proof of the theorem. For simplicity, we prove the theorem only in the discrete case. Suppose that the domain spaces of V and T are respectively denoted by script V and script T. Let for any small v belongs to script V, we write h of small v, which is probability under theta, v equals to small v. Obviously, hv is free from theta since v is ancillary for theta and therefore the distribution of v is independent of theta. Since t is sufficient for theta, the conditional distribution of v given t equals to small t is independent of theta for all t belongs to script t. This follows from the definition of sufficient statistic. Now let us write g of small t, which is equals to probability v equals to small v given t equals to small t. Let us write gt equals to probability v equals to small v given t equals to small t, where t belongs to the domain space of capital T, that is script p. Then we take the expectation of gt. Expectation of gt is equals to summation over small t belongs to script t, probability v equals to small v given t equals to t into probability t equals to small t. From the definition of conditional probability, we get summation over t belongs to script t, probability under theta v equals to small v comma t equals to small t. Note that probability under theta v equals to small v t equals to small t denotes the joint PMF of v and t. And when we take the summation over all values of t belongs to script t, we get the marginal PMF of v, and this is just probability v equals to small v, and in our notation this is equals to hv. It follows that expectation under theta gt minus hv equals to 0 for all theta belongs to script theta. Now t is complete means that there does not exist any non-trivial function of t which is an unbiased estimator of 0, and therefore expectation gt minus hv equals to 0 for all theta implies that gt equals to hv with probability 1 for all v belongs to script v and for all t belongs to script t. Thus, we see that the conditional distribution of v given t is same as the marginal distribution of v, and hence v and t are independently distributed. The implication of Basu's theorem is that if t is complete in addition to being sufficient, then no ancillary statistic other than the constants can be computed from t. Thus, by Basu's theorem, completeness of a sufficient statistic capital T characterizes the success of T in separating the informative part of the data from that part which by itself carries no information. Now, there are several ways to think of possible converses to Basu's theorem. One natural question is that if T is complete and sufficient for theta and V is distributed independently of T for every theta belongs to script theta, then is V ancillary? The answer is no, as it can be seen from the following counter example, which is due to Malloy Ghosh. Let x be a random variable with PDF. F theta x equals to 1 if theta less than equals to x less than theta plus 1, where theta belongs to script theta, where script theta is a countable set with point. Let x be a random variable with PDF. F theta x equals to 1 if theta less than equals to x less than theta plus 1, where theta belongs to script theta, which is a countable set with points 0, plus minus 1, plus minus 2, dot dot dot. This can be written as f theta x equals to 1 if box x equals to theta, where box x denotes the integer part of x. The distribution of box x is degenerate at theta, that is, probability under theta box x equals to theta, this is equals to 1 for all theta. It is easy to check that box x is complete sufficient for theta and it is distributed independently of x, but x is not ancillary. Now we consider some interesting applications of Bashu's theorem. In our first application, let x1, x2 up to xn be independently distributed rectangular random variables with parameters 0 and theta, where theta greater than 0. Let x ordered 1 less than x ordered 2 up to less than x ordered n be the ordered statistics from the sample. Then we have seen that the statistic V, which is the ratio of the largest order statistic to the smallest order statistic, is ancillary for theta. And we know that capital T, which is equals to the largest order statistic, that is x ordered n, is complete sufficient for theta. Hence, T is distributed independently of V. We consider the second application. Let x1, x2 up to xn be independently distributed as normal random variables with mean theta and variance 1, where theta belongs to real line. Then we know that V equals to summation over I from 1 to n xi minus x bar whole square is ancillary for theta, and we also know that x bar, which is actually 1 by n into summation over I from 1 to n xi, is complete sufficient for theta. Hence, T is distributed independently of V by Bashu's theorem, and we thus see that the sample mean and sample variance are independently distributed in case of normal theta 1 population. Next, we consider another interesting example. Let x1, x2, xn be independently distributed random variables which are normal with mean theta and variance 1, where theta belongs to real line. Now we know that the statistic x bar, which is actually the sample mean, is complete sufficient for theta. Let us write capital M, which is the median of x1, x2 up to xn. Then the statistic V equals to M minus x bar, which is actually median of x1 minus theta, x2 minus theta up to xn minus theta, minus x bar minus theta, because we know that the median of x1 minus theta, x2 minus theta up to xn minus theta is actually the median of x1, x2, xn minus theta due to the invariance property of the median. Hence, the statistic V, which is M minus x bar, has its distribution independent of theta. Hence, V is ancillary for theta, and therefore by Bashu's theorem it is distributed independently of the complete sufficient statistic x bar. Now we know that if two statistics are independent, they must be uncorrelated, and therefore covariance under theta x bar and v is equals to 0, which implies that covariance under theta x bar comma m minus x bar is equals to 0, which is in turn implies that covariance under theta x bar and m is equals to variance under theta x bar, which is equals to 1 by n for all theta. Thus we get the covariance between the statistics x bar and m by using the Basu's theorem. In the present lecture, we have introduced the idea of an ancillary statistic through various examples. We have seen that an ancillary statistic contains no information about the unknown parameter theta. An interesting fact is to be noted that a sufficient statistic for a parameter theta may contains a lot of ancillary material, that is the material which are irrelevant as far as theta is concerned. Therefore, a trimming of the ancillary material is necessary. A sufficient statistic can be considered to be good if it contains no ancillary material, that is, no non-constant function of it has distribution independent of the parameter theta. This leads to the idea of a complete sufficient statistic. Another interesting fact that we have observed from this lecture is that if a complete sufficient statistic exists, then it is independent of the ancillary statistic, which is known as the de Basu's theorem. Thank you.